All right, let's go back to our ambient molecule, draw it in the skeletal format, and we'll see how much better the skeletal format is. I'll give you guys some kind of hints and tips along the way, but the number one thing, honestly, is just practice, practice, practice. There's just no way around it. So what I would do is just pick one predominant part of this molecule, maybe this ring right here. You see it's a ring, and there's 1, 2, 3, 4, 5, 6. 6 things there, 6-sided ring. That's a hexagon. So we can just go ahead straight draw a hexagon like that. And you can see then we have alternating double bonds, right? Double bond, double bond, double bond. So we need to include those, double bond, double bond, double bond. And then we have this carbon group on the outside. We can just draw a straight line, right? That's an implication that there's a CH3 right there. And then over here on this left side, we've got it connected to a 5-member ring with 2 nitrogens, right? 1, 2, 3, 4, 5, right? The nitrogens are in positions 2 and 4. So we draw a line. There's our carbon number 1. Draw it up to a nitrogen, then another carbon, then down to a nitrogen, then another carbon, and then back up, right? And then pay attention to where the double bonds there. There's one there and then one there. So we need to include these double bonds. We do not need to include the lone pairs on the nitrogens. We can totally omit that. And then we've got this other section of carbons right here. So it's 1, 2, 3, 4 more carbons that are attached to this ring of a 6-membered ring, right? So 1, 2, 3, 4. There's our 4 carbons, and then add in the 2 double bonds. And then we can see that there's another carbon kind of hanging out here as well. So we can go ahead and attach that. Then finally, we've got this down area right here, right? We're attached to 1 carbon based off of this carbon right there. So 1 right there. Then connected to another carbon that's doubly bound to an oxygen, right? So there's that other carbon doubly bound to the oxygen. We don't have to include the lone pairs. This carbon is doubly bound to an oxygen and also bound to a nitrogen with 2 carbons attached to it. So nitrogen and then 1, 2 carbons. And that's it, right? And you can see how the structure on the right is a lot more clear than a structure on the left, right? It's not as cluttered. It may be a little confusing to you right now just because you're not used to seeing these structures, but once you get more used to drawing them, you'll get a lot better at them, right? And so here I Googled the structure of it. So you can see here it's kind of, done by a computer, so more nicely. And to be honest, my handwriting there was not the best. It's usually better than that, but whatever, we'll go with good enough, right? And you can see the structure that we drew matches the structure that I found on the internet, right? So you can draw this correctly. And again, it's really just practice. There's no way around it. You gotta practice, practice, practice. So you need to be able to see these skeletal structures and then envision what the molecule actually looks like. So let's take a look at an example of like this one right here. And there's different questions I could ask you, right? One question I could ask you is, what's the formula? What's the formula of this compound, right? So remember that each one of these intersections and endpoints is a carbon. So there's a carbon here, 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons, right? So the formula is C7. And then remember, there's as many H's as there needs to be. None of these carbons have a charge on them, so they all need to have 4 bonds, right? Carbon has 4 bonds. So 1, 2, 3, that's 4 bonds on that carbon. This carbon needs 3 more bonds. This carbon right here already has 3 bonds, so it just needs 1 more. This carbon already has 3 bonds, right? A single and a double bond, that's 3 bonds, so it only needs 1 more. This carbon also already has 3 bonds, so it just needs 1 more. This carbon already has all 4 bonds, so it doesn't have any hydrogens. And then this carbon has 1 bond, so there's 3 hydrogens. And so if you count them up, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, there's 12 hydrogens. And then, of course, don't forget about the oxygen, right? So you see how this structural component or the skeletal structure contains the same amount of information. Another question I could ask you is, what's the number of lone pairs? Are there any lone pairs on this compound? And so think about what's going to have the lone pairs. The carbon generally doesn't have lone pairs. And so we have to take a look at this oxygen, right? In order for this oxygen to be neutral in terms of formal charge, right, normally has 6 valence electrons, here 2 bonds. That means it needs 4 more electrons, or 2 lone pairs, right? So there's 2 lone pairs. Another question I could ask you is, what's the hybridization / the shape / the bond angles of all of these carbons? And you should be able to identify this relatively simply, right? This carbon, and this carbon all have 4 things attached, as well as this carbon right here. 4 things attached is sp3 hybridization. sp3 hybridization here is all tetrahedral. We have no lone pairs, and it's 109.5 degrees. This carbon has 3 things to it. This carbon also has 3 things attached, and so does this carbon, right? So they're all sp2 hybridized, and they're all trigonal planar, which has a bond angle of approximately 120 degrees. And then finally, this oxygen here itself is sp2 hybridized. It's not trigonal planar though, because it has lone pairs. It doesn't really have a shape by definition. I guess you could kind of think of it as kind of trigonal planar or linear if you want, but we generally don't assign shapes to terminal atoms. So there's one example. Let's take a look at another example. So again, let's ask kind of the similar or the same questions we did last time. So what's the formula here of this compound? And remember, there's a carbon at every intersection and endpoint, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons, so it's C9. Think about how many hydrogens. Remember, carbon needs 4 bonds, and so we can draw in the hydrogens there. So this carbon only has 1 bond, so it needs 3 hydrogens. So I'm just gonna put H3 there. Same thing, H3 here. Here, this carbon already has 3 bonds, so there's only 1 H here. This carbon already has all 4 bonds, right? 2 single and a double, that's 4, so no hydrogens there. No hydrogens there as well. These 2 carbons also both have 4 bonds, so no hydrogens there. This carbon has 2 bonds shown. Come on. And so that implies that there's 2 more hydrogens there. And then this carbon has 1 bond shown, and so there's 3 hydrogens there. So if you add those up, let's see, that's 12, H12. And then, of course, don't forget the oxygen, right? So it's C9H12O. We could ask for the number of lone pairs. And of course, we're going to look at our non-carbon atom. That's this oxygen. And this oxygen, again, needs 2 sets of lone pairs. So there's 2 lone pairs. And then we can talk about the hybridization of the carbons. So let's first identify all the sp3 carbons, all the things that are attached to 3 things. So there's 1 here, 1 here, 1 here, and then 1 here. So all of these are sp3 hybridized. If we're talking about sp2 hybridized, that's attached to 3 things. So this carbon, and this carbon, those are all sp2 hybridized. And then finally, we actually have some sp hybridized carbons, right? These carbons are attached to only 2 things, so they are sp hybridized. And this oxygen right here is sp2 hybridized as well. So I can do that very quickly because I've done a lot of practice. The only way you're going to be able to do it quickly and accurately is through practice. This stuff is really, really practice. There's no kind of, shortcut. Let's take a look at another atom. This atom wouldn't exist in real life. There's no way this thing would actually exist, but it'll serve our purpose to kind of get some more practice in here in a kind of constructive way. And so the thing I'm saying here is to be careful of formal charges. Be aware of formal charges, and be prepared for them, right? So the question is here, how many lone pairs do we have? And so first off, we start off with this nitrogen. Nitrogen normally has 5 valence electrons. Here it's only got 3 bonds, and it's neutral here, so it must have a lone pair. Oxygen normally has 6 valence electrons, and here it's got a negative formal charge, so it needs to have 7 either electrons or bonds around it. It has 1 bond, and so that means that there's an implication that there's 3 lone pairs here. Oops, I forgot to put that formal charge there. That should have been there originally, right? This nitrogen has 4 bonds and a positive formal charge, so that means that there's no lone pairs here. This oxygen has a positive charge and only 3 bonds. That implies that there's a lone pair there, right? So we filled in this structure with lone pairs. Again, I'm doing this very quickly because I'm very used to it. You guys just got to practice, practice, practice. Watching me do it isn't going to help you as much as doing it yourself. Another thing to be careful about is carbocations, right? So this carbon right here in this center, right? There's a carbon right there. If you think about the Lewis structure, right? There's a carbon and then a CH3 and then a CH3 and then a CH3 with a positive charge. There's no hydrogen there, right? There's no hydrogen there. It's got a positive charge. The only way carbon has a positive charge is with 3 bonds and no lone pairs, right? And so there's no lone pair there. And this is an sp2 hybridized carbon. This is trigonal planar. And then each one of these carbons on the end here have 3 hydrogens on them, right? There's a carbon here, carbon here, carbon here. Right, and so the formula overall would be C4H9+, right? And again, all of this stuff is just practice, practice, practice. That's pretty much all organic chemistry is. It's just basically like one big puzzle, one big game. The best way you're going to get better at it is to just do more of it.